And he's going to talk about parametric design. Welcome.
Thank you. Hi, it's a pleasure to be here. Actually, from what I can tell from visiting your workshop, what we deal with in our office all the time, and what I've dealt with myself, has been actually has a direct correlation to what you're doing. I mean, today, all I hear from like people in our office and our collaborators and people trying to push our industry, to be more adaptable and respond to the stuff we needed to. Everybody's talking about the process and the fact that everybody's stuck, making like satisfying the requirement to have 2D drawings and wanting like a greater collaboration between the different players in producing a building. And that's what we deal with all the time. But, so I'll get to that in a minute. What we've got here is a little introduction to BIG. Yeah. We started as BIG in 2006, and now we are. Let's start that over. Now we are spread over 2 offices. A main one in Copenhagen, where we're about 85, and then another 15 of us in New York, which opened in September. So there are actually some good possibilities for the North American market. But we're headquartered here in Copenhagen, and where we've addressed small issue stuff, like small scale stuff, like the harbor bath as plot in around 2002, I think. This is the VM houses, where we address the want and the need of everybody to have basic things like exposure to direct sunlight and have nice views and so on. Where each apartment is unique and has a south-facing panorama. Next door to that is the mountain dwellings, where you basically combine these two totally opposed, diametrically opposed urban elements like the parking garage and the apartment block, and by laying them directly on top of one another, with the parking garage sloping underneath the terracing apartment, everybody gets a view south, a nice terrace, a nice garden, and access to their car, even high 10 stories off the ground. And Jesses Moore came out as an exhibition at DAC, at the Danish Architecture Center, in 2009, and was then turned into a book in English, and now I think is published in around 15 languages. And we presented, I think, in the presentations in September. Just south of the VM and mountain dwellings is the big house, or the 8 house as we call it. It's the figure 8, which is 476 apartments of differing 5 different urban typologies arranged vertically, with a green path going around the top. And it's now completed and standing. It's not like around here. There's one building, there's another building, and the rest is unfaded. Like there's nothing going on in there. But hopefully someday it'll be infilled, and it really does stand on its own. But that's all Denmark. We went to China once and did the Danish National Pavilion for the Shanghai Expo in 2010, which I also worked on. We wanted to move her, and we did. We moved her for 6 months. We moved the Little Mermaid to Shanghai and gave her a house, and you've probably heard about it. It's conceived of as a continuous bike-friendly and pedestrian-friendly loop from simple geometric elements where you take two circles and just lift one up and connect it around the back. That simple move results in really complex behavior and gives a rich experience to the pavilion. And this is the first major building project where we started to use parametric modeling tools in order to address the fact that we needed to really dial in the right geometry and get the facades right and get the dimensions of the entire thing, like from the floor thickness and coordinating with our engineers for column placement and so on. That all had to be done at a really rapid fire pace because it was being built, or it was about to be built right when basically when we started the construction phase of the project. It all had to happen really fast, and the only way to deal with that was to have these generative tools going along the way. And under construction, we didn't use it, however, to define the full geometry because that had been set by the time that that people in the office who were familiar with the tools, like in our case, like Grasshopper and Rhino, they got involved. And the site dimensions were set by the pavilion, so we couldn't really do a whole lot about that. But what we could do was address how the facade pattern worked, and the really complex interiors where we have 6 different elements from. Let's see if we can see it here. Go back. From where you exit here, you have the entrance underneath. You have a viewing deck with facade, bicycle ramp crossing over, a pedestrian exit like fire stair. When you combine all those together, we had to use Grasshopper in order to solve them all, to get them all to fit. But that's the completed project, and it was actually pretty successful. I think it was really successful. I felt like when we took the entire office there, and the thing was, like, you were supposed to give the lady who was in charge of the bikes. We had a bunch of Copenhagen city bikes on the roof, so that you could ride in a continuous loop around the blue path on the roof and also through the interior, exiting out the bottom and re-entering the pavilion in the entrance underneath. You were supposed to give the lady about 100 kroner worth of Chinese money so you could get a token for which to use the Copenhagen city bikes, unlock it, and then ride around. But that token was a 20 kroner piece, so I happened to have one in my pocket. I just plugged it in and took my bike. Broke the rules, but when cycling was before the police shut down the cycling, which was a bit sad, it really did give you the feeling of being in a Danish city, where it's like a theater, basically. The bikes, the pedestrians, they all mix together and spectate the same city happening in front of them. And it offered a really successful, actually more than the entire population of Denmark's worth of Chinese people experienced the pavilion. It was over 5 million. And then again in China, we just submitted final DD, like detailed design documents for the Shenzhen Energy Mansion in Shenzhen near Hong Kong. And I'll get into this briefly at the end. But this is another project on which we tried to keep these parametric tools sort of accessible and active for team members, even who weren't involved in it. But like all projects, all of our projects start as a series of sketch models. And we believe in sketch models as a tool for the early stages of a sketch project, because they offer a more democratic way for more people to get involved in the discussion. Basically, an idea isn't believed until it's built at some scale, and you take those like an idea in model, and then that model is discussed and debated, and the more people exposed to that model, so you're not staring at a screen. Even though the computer is probably what generated the model in the first place, you build it in analog, and then that allows you to debate and fuel the debate for the next iteration of that model. So it's what we call like the recursive design process in the sketch phase of the project. That's when you push that process to happen more and more. You fuel the debate and fuel the iterations just exactly like an evolutionary solver or a do loop would in programming. There's no difference between it until you get the result. You get a result that makes the best fit for the criteria. So it's not uncommon. Like in this case, this was the scale of the tower project. This is 64 of the more than 100 models we just generated through in order to find the right fit for our criteria in an accessible way. So instead of having like a more traditional concepted as a linear process, we basically keep revolving the process through an accessible platform of the models. We develop our sketch and continue that process until we get a fit that solves what we needed to. Then we went to Kazakhstan, and that's really where we from China to Kazakhstan, we really needed to have an active, repeatable generator of those sketches from the sketch phase all the way through construction. This is the presidential library, the new presidential library in Astana, the capital of Kazakhstan. It's a 33,000 square meter, well, this is the official name of it. It's not the Astana National Library like we call it. It's the building of the official funded library of the first president of Kazakhstan in Astana, Nursultan Nazarbayev. It's a 33,000 square meter combination of a presidential library, which is an archive, a collection, with public functions worked in. And those public functions actually take up more space and offer the building as a node for the citizenry, where we'll combine activities like education and laboratories for students, and cinemas, and there's actually a prayer room and a presidential area exclusively, a bomb-proof archive area, all sculpted into one project. And from the competition phase, we found that when we surmised all the different criteria to address what a public library, a presidential library in Kazakhstan really was, we had to go back to, of course, the history of Kazakhstan, the tradition of nomadism, which defined the development of their people for generations, over thousands of years. And more recently, the move of the capital from Almaty to Astana in 1994, 3 years after independence from the Soviet Union. Same president moved the capital and wanted to focus more economic and social functions around Astana. And to leave new legacies for the Kazakh people. And that's where we came in with our winning competition entry. On the outskirts of Astana, actually, where if you follow this axis up to the president's workplace, you go from that axis down the way, you have the Norman Foster Pyramid, and on the other side, the Norman Foster Tent Project, more cultural icons available for the people of Astana. And the building isn't just conceived of as a bunch of shapes. Like the story the story of this project in particular followed something which could then be represented in a strong geometry. Not all the projects are like that, but this one definitely was. Where if you take the traditional way of indexing a library, the easiest way is to follow do a decimal system and organize it linearly. But when you turn it into an infinite icon, then it offers a more intuitive way to hold the ever-growing collection of books and internet and IT kind of stuff that the library is going to have. The public functions, though, are really what's going to attract most people to it. And by integrating those with the circular library, the circular form offers the most area for literal integration of the two programmatic types. Then by wrapping that program, all additional program, which far outweighs the floor area we need for the library, that was a way to expose all the areas of program to views of Kazakhstan, views of Astana, and to offer the most integration between the different types of program around this untouched library room. So it told the story not only of that, but of the Kazakh landscape, and of actually the Mobius strip, the symbol of eternity, of nomadism, which was the Kazakh people. And that's why we're all quite committed to this shape on this project. And if you wrap the internal volume with a shell that is actually sourced from the same geometry, then you can use it in winter as well. But it all started with this guy. This is August Mobius, the German 19th century mathematician who's famous. I mean, we know him more for the name of the Mobius strip, which is a single-sided surface. You take a piece of paper, twist it, and you put the ends together, then you get a continuous surface, even though it looks like you have a front and a back. But what was also important was that important for our building was that if you take what's called the Mobius equation, it results in a spine with a horizontal one side and a vertical on the other, and an infinite spiraling from an equation that we could then control with parameters. Those parameters are where that's controlling those parameters is where our burgeoning expertise with Grasshopper started to be important. The reason why we use tools like Rhino and Grasshopper instead of more like traditional building-oriented BIM tools or more expensive tools is because they're so accessible. Rhino is really accessible for people on it, for people who maybe don't know a whole lot about 3D modeling. It's really intuitive, and so that means it's good for students and people sketching in our office. And Grasshopper for the same reasons. There's not a really high learning curve to producing it. So by getting those parameters and making them available to people on the team, we can adjust that Mobius spine and extract what we need from it in order to produce the base of the building. So you plot those points, adjust 3 parameters, and get the source of the interior volumes, see it on the left, and the facade shell, which encases it. And we can make them constructible that way. So we just extract some center lines, and the center of this, and the center of them, of the spine is always a circle. That's where sine and cosine equal each other in the equation. You extract those center lines and plot points at a reasonable resolution for construction in the end. The spiral wraps around the circle. You extrude the volumes and cut it into decks. And those decks, spaced divided radially, are where we'll house the program. And that same spine gives birth to a series of radially oriented rectangular frames for the facade shell. And by taking these rectangles and essentially sweeping them around the circle of the interior, we encase the program. But because we're using rectangles, then that means we can make it more easily constructible. So part of the surface in one way responds, like it behaves as a traditional doubly curved, more arbitrarily defined surface, but we can build it out of straight elements. I mean, straight steel members, the structure makes a lot of sense. And more people are more happy because of it. And that means, constructors, engineers, everybody down the line. It makes a building that makes a lot more sense. And that's how we define it. We've seen Grasshopper definitions, and it's as simple as that is. But it was important to keep this active through the whole process. Because, in order to produce, this is an early sketch model at 1 to 200, but before we even got there, before we actually even signed the contract to start the project, this was in September of 2009, we flew to Astana to sign the contract to start the project, and found out that, from the competition phase, we moved the site, and we dug a hole, and there was no architecture done, no engineering done. We just decided to make a piling plan. We meaning people carrying us around Kazakhstan. They had decided to build, to cover our presentation boards, our 1 to 200 plans with a circle. The building's not circular. To cover it with a circle and say that it was probably enough to sink about 3,000 30 by 30 centimeter piles, concrete piles, 6 or 7 meters into the ground, and cast a 1 meter raft on top of it. That should be enough to hold up whatever we end up designing down the road. And it really happened. Like this was, I think this was in October, or no, this was probably in November of 2009, when like we could, having that the grasshopper definition available to us to sketch and reproduce the changes that we needed to produce in order to get the proportions of the building right, to get the gross floor area right, to get the section height correct for people to walk in, all the things you have to take into account to get the building more or less buildable at this early stage was happening while they were sinking piles. And that meant that, having that available, that parametric model available for us to generate those fit options was totally critical. And like, maybe they got a little enthusiastic. They hit the piles a little too hard, a bunch of them. But in the end, it was actually, it actually ended up being enough for our scheme. Despite the fact that we had to, from the competition phase to the construction phase, we had to reduce the gross floor area from 40,000 square meters in the brief down to 30,000. And of course, that's fine, except let's go here and produce something completely engineered and ready to go on the way. So you can see these piles down here. Those are the areas that we needed more than just the standard 30 centimeter, 6 meter down piles that were going to be placed anyway. So we had to define along the way, like as they were piling, where the cores were going to be, how many cores we were going to have for a 30,000 square meter building under construction as we were sketching. And the concept is pretty simple actually. That we have cores suspending the ring of books, as we call it, the library collection, and suspended from the library collection, both in a programmatic and in a structurally literal sense, is the spiral which wraps around. And so, the thing about scaling a building down is that you can scale it. You can scale the building properly planned in order to get the right floor areas for costing, production, and everything. But you can't scale it in section. You can't scale a building in section because you can't scale a person. You can't really scale steel members so much. So, in order to retain the original qualities of the sketch proposal, we had to completely rethink the building and completely recreate our concept of the section and have more divisions of each volume, and that kind of thing was taken under, was done while they were piling, while they were ready to build, while we were solving the most critical architectural elements of it under extreme duress. Had to go to Grasshopper, had to go back to the equation. We had to keep that active. But we managed to do it and have a completed, finalized basement plan, cores set out, everything ready to go by December or January of that year. And we continued developing the project where we had the internal decks surrounded by our structurally sound shell, which was engineered by our engineers in New York, where we had the internal superstructure engineered by a company in Britain. So they had to communicate with each other. We had to communicate with both of them. In fact, our British engineers, while the Kazakhs were driving piles in the ground, they actually sent 3 of their 3 of their employees to work with us in our office at our desks, so that we could have, so we really wouldn't lose any time, because we had no time to lose producing this thing. And so by March of 2010, we were ready to push it to the next level and do our next submittal. But then we found out that we actually had to, with some additional programmatic requirements added along the way, we had to go back down from what ended up being 33,000 square meters down to 30,000. We had to reduce the building again, but we lost one of our parameters. We didn't have the radius. The radius was set by the fact that the cores were set in plan. That stuff was already built by the basement plan. So we had to retain the original qualities of the geometry without scaling the section, without scaling the plan too much, and without losing it. But by keeping our grasshopper definition active and our familiarity with it active along the way, there were a couple of guys managed to do it in a weekend, and then be able to reproduce the whole building. Ultimately, thankfully, that was only a threat. We redid the whole building. We were ready to have the base geometry ready to produce the rest of the documentation for the next, the redoing of the phase we had done. Luckily, we didn't have to do that, but the threat was always there, and that threat has sort of like been constant throughout the project, and so we definitely had a reason to keep it active, even when the whole thing's engineered. When this is some calculations from Front in New York. They engineered our facade, and that engineering of the facade produced some real numbers that we had to account for in the superstructure. There's a lot of back and forth going on between the different players, and that back and forth basically, crosses a point when you can't go back to the original equation, right? That we actually ended up having to. That structure is going to hold up the facade, and that structure has dimensions that can't really be changed. And in the end, we produced enough defensible stuff for that sketch to continue with the production of the project. And that production actually is where we opened up the, like when we're trying to finish the glazing on the facade, determine the glazing system, the internal facades as well. We needed to open that up to more members of the team than just the few people who kind of knew how to run grasshoppers. So that's where we started. Yeah, we use Rhino and Grasshopper for this stuff in order to make stuff that's like accessible for the whole team. That's one of our core principles that we want to keep going through all phases of the project, not only through the sketch phase. So here, where you can see our generally our south-facing area here. This is the solar radiation for the year, and this is what would end up driving, in one way or another, the way we treat the facade. And what we wanted to do was open the development of this to more people than just the ones who could operate it in 3D. So of course we unroll the facade. We turn that into actually into a Rhino script that would analyze the luminance values of a 2D image, so that people could basically adjust the porosity, the opaqueness of the facade in different points by doing it in Photoshop, which they were more familiar with. They could do their studies in a raster image and then translate that into, through our script, that would translate into windows on the facade. And this is a sketch we actually didn't end up going with. We ended up going with a different option, but this illustrates the fact that we want to open it up to more people than just the ones who might have the necessary skills to deal with the numbers and the code. So in this early sketch, we would have the openness of a triangular panel, like how much glazing is on a certain panel size, be determined by how black and white the input image is. So we open it up to everybody on the team, and that results in a sketch that we can then analyze, discuss, and then decide if we want to keep it, discard it, or do whatever in the sort of traditional way. In the end, of course, actually not of course, but we didn't actually go with this option because it was technically a little bit impossible. however dramatic it might be, we ended up going with the fact that we needed to just have glazing, just pure glazing as a skin around the radial frame structure. And the way we treat the glazing would then reflect how we study the opacity of the facade panels in 2D. But maintaining, there's a lot of information to maintain in a building like this. I guess you guys have been dealing with that a little bit in a short 3-day workshop, and maybe in other things you do as well. But a building has a lot of information. And what we needed to do was keep our building, like I said, active, flexible, adaptable, and cheap. We didn't have the time or the money to devote to training people to using tools that would normally be used in the production of a complex and large building like this in the non-Western world. So keeping, there's a lot of data to manage, and you had to sort of keep an iron grip on this because what we ended up producing was a lot of 2D drawings, 2D studies that did not really reflect the complexity of the facade geometry. Basically what we do is we have a model in Rhino that is available to everybody, which has a series of references and so on that everybody has access to. And that model was set in the early days straight out of Grasshopper. Whenever we get a sketch, we finish it and then offer that pure geometry as a reference. There are a few ways to do it, and we did it in the way we had, which is a really cheap, really powerful tool. And so all of this information, like the plan, center lines, and so on, all that stuff was set once, straight out of Grasshopper, never changed. Next time we did the building, we redid the whole thing, set it once, don't change it. And that way we give everybody a tool that they can rely on to produce their 2D drawings down the line. So keeping everything sort of wholly and complete at the beginning, at the source, is a way to keep all that is produced from it. It retains all the information all the way back. So you can see the original equation in every one of these models produced that's present as references for everybody. So these dimensions, those are the parameters we work with. We set them, forget them, redo it again, and that was a way to expose the building process of the 3D to more people on the team. Because everybody making decisions on the team, and everybody makes decisions in this process, they all had to have a strong understanding of the geometry, and this was a way to make it available for everybody. We set our radial grid lines at a spacing that produces a good slope for handicapped accessibility and for the stairs. And in the end, we have a series of models that we can then build up from actually including the landscape. The facade follows the same concept. I mean, we kept this all in-house. That was another thing that was important for us, working under a short time crunch situation, was to keep the development of our facade, of the different elements, choosing which elements we needed, seeing how, actually in this case, how twisty the facade is, how the coincident angle of the glazing system on top of the structure, keeping that active, keeping that in our control was really important, because if you, in our situation as architects, like our engineers told us, we need to hear from you what your concept is and what you need, because if we have to guess, we're probably going to guess wrong. So we need to participate in a dialogue with you along the way, and that dialogue for them meant hearing what we wanted. Then when we were able to produce what we wanted to see, without waiting for somebody else, without having to pay for somebody else to do it, that was really critical. Because then we could end up getting the project we wanted in the end. And this is the facade system, built up from a series of model templates that, again, were set and offered as templates to the entire team so that they could use them in order to produce whatever they had to produce. It didn't matter what tool they were using. It doesn't matter if you use Rhino, Grasshopper, or whatever. Use what works best for whatever you have to do. And so I think when some better tool that suits our needs better comes along for us, we'll use that. But until then, nothing we found has been as cheap or as powerful or as accessible to new users. Where you can start to study stuff in 2D from a 3D model. And this is all controlled using in-house expertise, which was developed along the way. We didn't have it when we started, but now we have it. And actually, this is a pretty interesting way to get to solve impossible issues. Let's see if we can see it here. This is what would become an unrolled elevation. Now we didn't use it for any final drawings. So along the way, it was just this was a really powerful sketching tool for solving where the facade shell meets the landscape. A twisting facade meaning an undulating landscape. How do you determine where to place the elements of the concrete base wall detail underneath? I can't do it in 3D. There's no way. I mean, you could come close. You could come close to sketching something, but in the end, you need something drawn in from the 2D, like sketched in an easy way, a more accessible way that you can deal with and understand. So basically, what you do is unroll the elevation and find the intersection points that you want in 2D. And using Rhino scripts that we developed ourselves, we could sketch, make a slope, draw a slope line in 2D that we like, and then reapply that back onto the 3D. And then we get our solution. So in the end, what we had was a really complex model. It's actually a simple model, but there are lots of complex, lots of layers of information to it, like any building would have. And that's an example of exactly what I was talking about, where you have that intersection point. I don't even know where you would find that in 3D. It's not possible. There's no way to set it up. There's no way to draw it. But having the expertise that we had in our office to produce it made it possible for us. So if you lay all that stuff over itself, you get something as simple as the facade shell to a series of templates that you can use to then produce everything you want. This is our structural wireframe that we produced ourselves as the architects, because our engineers told us if they were to produce it themselves, it would take them about 2 months to build it from scratch in CATIA, and we did it in a couple of days in Rhino. Partly because we knew the building, but also because we are choosing a tool that is kind of easy and intuitive, but produces the same powerful result that they can then use down the line. And again, it doesn't matter what you use, just as long as you're comfortable with it, and it does what you need. So that interaction between the engineers, our different engineers, and ideally down the road our constructors, which we didn't really have because like the way of working in Kazakhstan is different from what we expect here in the West. That collaboration was sort of ongoing. I mean, you deal with that. You're dealing with that in your workshops until now. Sometimes, what originally exists as the scope of one guy will sort of get wrapped up in the scope of another guy. And basically, the idea is that you want to work together with each other to get this stuff to work. Of course, the format for what you choose, like the tool you choose for interchanging information, is important. But what's more important is that you like sort of maintain the spirit of wanting to do it. So in the end, I mean, we produced all our sketches and all of our architectural information from just numbers we got from our engineers. There's a series of radial frames here, 36 rectangular frames built from straight elements. Between them, this is as we discussed the concept, different structural concepts with our engineers to get them right, to get them to jive with what we saw as the vision of our building. This is a series of cross braces which follows the panelization of the glazing on the exterior, the layer above this. That holds up the whole building with beams twisting around the corners. And then the support material for the glazing layer is held in these radially placed, what we call subradials, with the glazing layer on top. There was, I believe, 27,000 square meters of facade glazing area and 33,000 square meters of total building area. It became a very expensive building, but again, this is stuff we all built in-house. We built all in-house. The thing is that, I mean, we had straight elements. You see the blue stuff is all straight, but when you add something simple like thickness to members, you realize that while the radial members might be straight, the corner beams and the cross braces, they all have to twist. And they all twist uniquely. And there's no way, I mean, even if they're set out with arcs, and we set them out with arcs, so there would be a way, hopefully an easier way to produce them down the road. Again, something that we would normally have discussed along the way with a contractor, but we didn't have access to them. We just basically had to do what we assumed down the road would make a better choice. And those choices actually were all more or less the right ones that we see in hindsight. Like, the simpler you make the decisions at the beginning, usually the easier the result is for people down the road, from the next engineer to the contractor to the guy putting it up. When you add thickness, all 6,000 of these, or actually there weren't 6,000, 1,200 of the cross braces have to twist uniquely, corner beams as well. They have to twist in order to meet the facade surface, the glazing surface, as a surface. Even though it's set out from arcs, you got different twisting. You can see it kind of starting to twist there, and it twists just a little bit, but enough to make it worth understanding. By keeping this in-house, again, this is where we retain the knowledge, along the way, really rapid fire style, because we had no time in order to wait a few days for an answer from a collaborator. We had to keep that in-house and make it ready for the next guy down the road. And the facade actually gets a bit dramatically twisting in some trouble spots. And those trouble spots were discussed at length with our, over a lot of meetings with our engineers who were in New York most of the time, or Bristol the other part of the time. And again, we would have had a lot of collaboration with contractors, but they weren't made available to us. So that was a sort of one element of the team that was kind of missing along the way. Because nobody was sure who the contractor would be, what their capabilities would be, who would be appointed, if there would be a tender process, all unknown. So we controlled what we could. And that included actually like determining where to place the gutters on the building, how much water runoff there would be. We had engineers, we had building services engineers of a different part of the company who were handling that for us, but we found that they required from us the knowledge of where the water would run on the building. This is just a simple thing we did in Rhinoscript to do it, to determine the liquid flow on a surface, fluid flow. Really, if there's only gravity to deal with, because who else would do it? We would have to pay for somebody to produce that kind of information to understand it, or we could do it ourselves and get the result in-house. And that's where some surprising results came out, where there's a dead spot, a watershed here. Water moves that way, even though the hemisphere of the building, the horizontal line is this way. The facade twists so dramatically that there exists, look from the top, there exists actually a watershed going down around here. It's something we had to find out for ourselves. The only way to do it was by doing it. That blue line is where the water decides to go one way or the other. And that's the information that we ended up feeding to our engineers, because there was sort of no choice. Who would do it? Who would have the knowledge? If you don't have the knowledge, sort of go after it and sort of get it. And if you need help, then you ask for it at the right places. And that's what we did along the process. A very short process. this is, I believe this is what, last summer? No, this was in autumn of this year, when we moved the entire team to Astana, in order to really get a grip on the project, on the submittal of some of our final DD documents to, well, what amounted to DD, to the authorities in Astana. And nobody expected, you could look at it, you could imagine it from like looking at the 3D model that there was actually a lot of water going to collect there, and that's what we wanted to make sure that we could handle. But then, this was sort of a way to say that we didn't have a tool available to us with the right level of expertise that would be enough to produce all the material that we needed to produce to get the building approved by the local authorities. Of course, you needed, if we're, right now the project is in a state of, it's a little bit on hold. It's under construction as far as we know, but it's a little bit on hold as well due to budget concerns. But what you really want to do with a building like this is to have a deep understanding of, you basically want a complete BIM model. That's a weird word to use, but a complete model that all the different players in the building construction can deal with. That's the best way to compile all the knowledge you need to for a complex geometry project. You can't describe everything you need to in 2D. On the other hand, we also needed to understand it in 2D. We needed to understand the sections, how they're being built, in order to represent them properly for not necessarily for the construction, but for the approval process. And that way we actually sourced everything from Rhino and exported them using Rhino script. We'd source everything from the model and you'd give it down the line to the people drawing in 2D for the required stuff. Keeping that model really, really crisp, holy, and untouched, and reliable was absolutely important, because we had no time to screw it up. There was no time to make a mistake. We're dealing with people who needed to build the building last week, and all of our collaborators we talked to always told us that our deadline was impossible. You can't do it. There's no way. But we sort of tried to defy the odds, and through a lot of rigor and a lot of focus on the process of maintaining good communication between the different players, between the engineers, between us internally, people working maybe more in 3D, people producing sections, some guys doing the material selection. By keeping our dialogue active, as much as we kept our grasshopper definition active, that was really the way we negotiated the impossible deadline, which changed along the way, which added new budget requirements, new programmatic requirements that we had to meet in space that we didn't have. All those things were happening concurrently and required a lot of good dialogue between everybody and between us and the computer. So in the end, we get everything from this finished building section. Had 1 to 200 to the analysis of the facade paneling and so on. This is all happening all at the same time. Or here's a design decision happening while we're finishing the sections. We're determining how the different divisions of the facade surface could result in panel dimensions which are more or less equilateral. Like, how perfect are the triangles? How much problems are we going to have down the road when we have to manufacture the facade panels with a manufacturer we don't know yet? Keeping this in-house, making it available to everybody in the drawing form is totally critical. I say this over and over, but I'm saying it's really important. You have to make the process available to everybody in order to get the right result evolved. So in the end, we can come up with in-house, we produce our own drawings and can set out the dimensions of what would then become shop drawings of the manufacturer. We keep it all under our control because it has to be under somebody's. 1 year after they dug the hole, this is where we were. This is September of 2010, where we had pushed through some final submittals. The rest of the superstructure, which you don't see here, but the basement was totally wrapped up, the concrete of it anyway, including some complicated stepping elements for meeting that facade slope that I was describing earlier, and an extreme amount of rebar, which you cannot imagine. That, of course, made it impossible for us to specify that we would, drill into the concrete in post and sink bolts with epoxy in order to mount the facade structure. That wasn't really possible because of all the rebar we had. We had to do it right the first time without really knowing what was going to happen next. And then, before we knew it, the superstructure steel was being delivered on site. This is for the Ring of Books in February of this year, where they had the entire, this is a 34-meter radius, all the radial bases for the cross brace girders of the Ring of Books were already laid out and ready to be built up. That doesn't mean, though, that we haven't forgotten about the equation. I took this last week. Due to budget concerns, we were not sure, but we might have to go back and redo the entire superstructure, leaving the basement alone as what it is, and retain whatever qualities we can retain. We want to retain of the geometry for a version of the superstructure which is reduced by around 70% from the original scheme. A completely different building happening right now. I'm actually going to be working on it on Sunday. So basically, you never really know what's going to happen, and staying flexible along the way and keeping all your tools available to other people who may not have the right, may not have the skills yet in order to manipulate what they need to. That's really what's making it possible to, through a dialogue, create something that we're going to build. So definitely stay tuned for that. As a sum up, I'm going to talk a little bit more about how we use Rhino and Grasshopper on the Shenzhen energy management. This was definitely a more orthodox project. Like, the geometry wasn't as complex, but we still needed to broaden our, to make our toolbox bigger. Like, we needed to have the ability to, in China, under again an extreme deadline, to produce a facade which responds to the site requirements, more or less, and the programmatic requirements inside. So in Shenzhen, in the financial district, we have basically the building volume is given to us. Like, the client needed tall towers, a tall office building, and we couldn't have the height of the building violate the local context. The solar orientation gave us a reason to produce a facade which responded to the view and the solar gain concerns of the occupants. As you deform the building to have on circulation levels and more public levels where you want more of a view to the outer context, and to expand the ground lobby in order to get more required area, we deform the building and then take a traditional facade and angle it so that the office occupants who don't like direct sunlight but still want a good view, you change one orientation of the facade to be opaque and one to be glazed, so that you can look out one and be protected from the other, as a general rule. But again, here's where we, through a toolbar that we offer to other uses of the project, this is the running of a really simple script that negotiates the difference between that zigzag pattern that works well for the office space and the places where we needed to flatten out and deform the geometry to make a flat, flush facade. So basically what this script does is it simply negotiates that surface, that twisting surface from the normal ziggy down to something flat, in a way that anybody can run with this toolbar. So that exposed the process to more people and made it more possible to get a more often produced and better evolved result from it. And it does simple stuff like classifying the degree. Actually, the next one will show how you classify the twisting of these facade elements into different modules with different ranges that are suited for production. Again, by keeping this information in-house, so that we knew what we were going to end up producing, that was really the way to get the most productive dialogue with our engineers. Again, not in-house. We didn't have like a direct dialogue with them at our desks, but we had a close dialogue with them overseas. We could find out where exactly our problems were going to be by running that script, and of course it classifies it into different layers, and then that can then be translated into something everybody gets, which is, this is black so you can't see it, but where the building information is turned into a drawing. And those drawings are then accessible by everybody, including local authorities. And we take that all away from a simple toolbar into the production of the drawing. We do that all in-house. But by recognizing that these new tools available to us, these parametric modelers, like a generative computational approach, we realize that is really symbiotic with how we feel about our sketching process and about all of our processes along the way. Like, the more we keep them flexible and evolving, and the more we iterate through options, of course, maybe in a traditional way, but using less traditional tools, opening that up to more people, and more access, and more debate, that's how we get the better result in a completed project. So this will be happening. We should be under construction sometime later this year. Hope it's as beautiful as this one, so it needs over. But that's what I got for today.